Okay, so this is part 4, final part. I thought the last one was the final part, but now we're looking at part 4 of function analysis. Okay, and a lot of the stuff we've just been developing this intuition here, but the idea of what we're looking for is, we're interpreting the derivatives and these critical values. And this is one of those moments where I'm actually going to review something before we get started into it. But the idea is if f prime changes sign where it's positive before and then negative after, then we're hitting that maximum. This is meant to be negative, red. And then if we're negative before and then positive after, then we're going to hit that relative minimum. And then the idea for points of inflection is just a change in sign. So those are kind of like the change in sign. If we change positive, negative, or negative, positive, we have point of inflection. We don't really care which way it changes. We just care that it does change. Okay. So this part of the notes is kind of a summary. It does give you tons of detail. I'm going to give you a more simplified version of that, but if you need to go back and get some more explanation, consult this section of the notes. And this is key right here, this thing right here. If there is no switch in signs at C, then C is neither relative min nor max. Even if the derivative is 0, even if it does flatten out, there is no min or max if there's no sign change. So let's talk about how we can calculate a sign change very easily. So let's review some pre-calc. In pre-calculus, you guys did stuff with functions. For example, if f of x equals x to the fourth minus x squared. And then you said, all right, we could factor that, I guess. We could factor that, no problem. So we're going to factor out x squared, and then we have x squared minus 1. And we factor that further, and we have x squared, and then x plus 1 to the first power, and x minus 1 to the first power. And you're probably asking, why is he saying to the first power? Why does that matter? It's going to be apparent here in a second. When we do this, then we try to find zeros or roots. What we're looking at is we know that x equals 0. We also know that x equals negative 1 and x equals 1. We have 3 roots there. And so if we were to draw a graph of this, let's make this a little more accurate with a horizontal line. Perfect. Oh, that's not what I want. I want a horizontal line. There we go. Horizontal line. Delete that. Then I'll do a vertical line to match it. So we have roots at 0, negative 1, and 1. So we're right here at 0 and at negative 1 and 1. But these roots are different because notice that the multiplicity or the degree of each root is different. The degree for this one's 2. The degree for these other ones is 1 and 1. These are linear roots. And this is a quadratic root. How does that matter? Well, if we were to sketch this curve, it would look, oh, not like that. Let's take that back. It would look like this. And now I'm going to color code these. So linear roots look like this. They go straight through. But quadratic roots, they don't go through. They hit 0, and then they just bounce off. These kind of bounce away. And you might be asking me, well, why does that matter? Why do I care? Well, I'm going to be doing a lot of roots here in a moment where we find when things equal 0. But then the question is, do they change sign? And how do we know something changes sign? We know it changes sign when it goes from negative to positive, or from positive to negative, or it passes through. But if it just goes from negative back to negative, or positive and stays positive, then it doesn't change. It doesn't pass through that 0. It just kind of touches it and says, see you later. Positive, positive. It's positive, hits 0, and then goes positive. It's negative, hits 0, and then goes negative again. But there's no sign change. It doesn't cross the x-axis. It doesn't cross this x-axis here. Why does that matter? Because we want to know about sign change. Sign change tells us relative max or min. No sign change tells us nothing. In fact, it kind of points more to, like, could it be a point of inflection? Probably. But as far as max or min, those require sign change. So we're going to see how this helps us when we look at some of this analysis. Let's look at the first one. So right now we have x cubed minus 3x squared. The first thing we got to do is look at critical values where f prime equals 0. So we got to start with f prime of x. F prime of x in this case is going to be 3x squared minus 6x to the first. If I were to factor that and set it equal to 0, I would have 3x times x minus 2. Okay, so now what I want to do is compare the roots. So I see that x equals 0 in this first one, and also x equals 2 in the second one. So I'll make a little chart, a little x and f prime of x chart. And I have to compare 0 and 2, and what's happening in between those. Because I know at 0, the derivative equals 0. And at 2, the derivative equals 0. But what happens before 0? For example, if I were to plug in negative 1, that would be negative 3 times negative 3. And that's positive. So if I were to look at negative 1, this is a positive value. So what does that mean for my slope? It means that I'm increasing. And then I flatten out. Well, what's happening between 0 and 2 then? Let's try 1. 3 times 1 is 3. 1 minus 2 is negative 1. So if I were to try 1, that would be negative, which means then I'm decreasing. Then for this next one here, let's look at what happens after 2. Plug in 3. 3 times 3 is 9. 3 times 2 is 1, so that's positive. I'm increasing, and I'm 0 in between. And now it should almost be obvious. You look at this and you see, oh, so at 0 I have a max, and at 2 I have a min, because I'm going up and down. So how do I write that in calculus? Well, this is how we would write it. We would say f of x has two things. First, a max at x equals 0, because the derivative, f prime of x, changes from positive to negative. So your answer comes in two parts. You're answering where it has the max, what it has and where. But then you also have to say why. So we got more information to add here too. We also would say f of x has a min at x equals 2 because f prime of x changes from negative to positive, or decreasing to increasing. Excellent, 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 excellent. Now we got one more thing to interpret. So now we want to look at points of inflection. We found maxes and mins. How do we find points of inflection? Well, that has a lot more to do with the second derivative. So let's start with that. Second derivative, in this case, f double prime of x. Let's look at what our first derivative was. It was 3x squared minus 6x. So this is going to be 6x minus 6. When does that equal 0? Well, if we factor this, we get 6 times x minus 1. So x equals 1. So now I got to compare the values of f double prime of x before and after 1. So here's 1. We know it's 0 there, but let's look at it before and after. See if we have a change in value. Do we switch sign? Well, before 1, like let's say I were to plug in 0. Plug in 0, you get negative. And after 1, let's say I plug in 2, I get positive. So I do change sign. So that means f of x has a point of inflection at x equals 1 because, so now we're saying what happens where and now why. Because f double prime of x changes sign. And we don't even have to be specific as to which way. We just have to say changes sign. All right. Is there anything else for us to do? Oh, confirm by calculator. Let's go ahead and do that. We have a calculator here. We're going to plug in this function. It's x cubed minus 3x squared. So x cubed minus 3x squared. And I'm going to just change my zoom to zoom standard here. Let's see what happens. That looks totally true. It's, it's increasing. We have a max here at 0, a min at 2, and right there at 1, it looks like we have a point of inflection. Let's zoom in just a little bit. We can change our x values at least from, let's say, -4 to 4, -5 to 5 maybe. So -5 to 5. We could even change the y values the same. -5 to 5. Gives us a little bit better picture. So I'm going to throw this in here just so you guys can really see what was happening. I'm going to shrink it way down. So that's what we saw. Excellent. All right, let's do part B now. First thing we got to start with is that first derivative. So that's where we're going to find our critical values. So f prime of x, the first derivative in this case, is going to be equal to 12x squared minus 4x cubed. Now, to find these critical values, we want to set this equal to 0. I'm going to factor this as well. So I'm going to pull out a 4 and an x squared. Then left over, I would have a 3 minus x. Is that what we got? I guess so. 3 minus x. So what does x equal in this case? X is going to equal 0, but it's also going to equal 3. Now here's where it gets a little interesting. I'm going to do this one way. I would encourage you guys to kind of put your pencil down and watch for about the next 3 minutes. Now I'm going to do it a completely different way that's much more faster. And you'll see however you want to do it. You can do it either way. But just go ahead and put your pencils down. Just kind of watch for a couple minutes here. So if I were to compare what's happening with x and f prime of x around these 2 points, let's see. We're looking at 0 before and after, and then at 3 and before and after. We know at 0 we're 0, and at 3 we're 0. So let's pick some numbers and plug them in. If I were to plug in -1 before 0, that would give me a positive in that first term and a positive in the second term as well. So that's going to be positive. Now if I were to plug a number in between, like 1, that would give me a positive for the 4x squared, and a positive again inside for the 3 minus x. That's positive as well. No sign change there, so nothing happened at 0. No relative min, no relative max. And then from 1 after 3 here, so plug in, let's say 4, we're going to have a positive times a negative. So that's going to be negative there. So we have our slope then. We're looking at this, it's going up, we're going flat, then we go up again, then we're flat, and then we go down. So we have a max here, but nothing at 0. Okay. Well, then I guess what we could say is f of x has a max at x equals 3 because f prime of x changes from positive to negative, which means that f of x, your original, changed from increasing to decreasing. So that's all we could say about max or min. And now let's look at points of inflection. Okay, so we got the maxes and mins out of the way. Let's look for points of inflection. So points of inflection, we take the second derivative, which would give us 24x minus 12x squared. So f double prime of x is going to be 24x minus 12x squared. We're going to set that equal to 0 and factor. So we can pull out a 12x, that gives us 2 to start, and minus x here. So now what's happening? We see that x equals 0 and x equals 2. So we got to compare before and after for those points. So we're looking at x and f double prime of x. So we're going to look at 0 and then at 2, before and after each of these. So at 0 we're equal to 0 and at 2 we're equal to 0, but the true curiosity we have is what's happening before and after. Okay, so if I'm looking at before 0, let's say negative 1, I plug in negative 1, that would be negative 24 minus 12, so that's going to be positive. If I plug in a number in between here, that's going to be positive 24, or wait, that's not positive, that's negative. Crazy, Mr. Butler. Let's take it back. That would be negative. So this is negative. Then if I were to plug in 1, that would be positive. And after 2, if I were to plug in 3, that's going to be negative. You can confirm that with your own calculations, or you can trust me either way. But now I know that f of x, the original function, has a point of inflection at x equals 0 and x equals 2 because f double prime of x changes sign. Right. So I'm going to do this here real quick. Let's insert a new page. Insert page after. So I'm going to keep that page there. If you want to go back and look at it, that's cool. But I want to take a picture of this and reuse it. So we're going to take a picture of this piece here, put it on clipboard, go to the next page, paste it here, there we go. Okay, so we're going to look at this function. I'm going to do it probably what I would call more efficient or faster method. But think back, just 2 or 3 pages back here. When we're talking about these, where do we change sign, whether it's a linear root or a quadratic root? So when we take the first derivative, so I'm redoing this problem but with a little bit of accelerated analysis, we get 12x squared minus 4x cubed. Now when I factor it, this is where the acceleration comes, because I pull out 4x squared, and then I have 3 minus x. So I'm going to look at these two roots. This one here, this is a linear root, and the other one here, this is quadratic. And in fact, it's not just linear or quadratic. It matters if it's odd root or if it's even. So what's going to happen with the odd root? Whoops, go back there. The odd root, this is going to be a sign change. I need to check which one. The quadratic root, no sign change. So I don't even care about that one. I just really care about the other root. So let's check it. If I'm just looking at 3, and what's happening before and after it. Now I just have to check this one number with x and f prime of x. So let's pick a number before 3. I don't know. Let's pick 2. So we plug in 2, and what do we get? We'd have 3 minus 2 and 4 times 2 squared. So we plug in 2 into this and we'd get a positive value. And we know it's going to have a sign change because it's 0 here, and this is a linear root, so then if we plug in any number after, it's going to be a sign change. A sign change. Why? Because it was a linear, an odd root. But why did I even need to check it? This is why, because I needed to know what kind of thing was it. It was either increasing then decreasing, which it is, or it could have been decreasing then increasing. And we know that it's the first one. So it's a max, which we just checked. And then even cooler, check this out. For the points of inflection, when I find f double prime of x, we know that's going to be 24x minus, what was this, 12x squared. And then when we factored out, we pulled out the 12x, and we had 2 minus x. Look at both of these. This is linear, and this is linear. So what does that mean? It has a sign change. Sign change. I don't even have to analyze anything. I could just say there's points of inflection at x equals 0 and x equals 2 because there's f double prime of x has a sign change. Sign change is all what we're talking about. When does it go positive? When does it go negative? When does it change? When is it 0? That's it. So much faster. And a lot of it had to do with that idea of understanding linear or odd roots or quadratic or even roots and the difference. Quadratic or even roots don't change sign. Linear or odd roots do change sign. So now, let's look at this. Oh, we got to do this best fit, fit the width. There we go. Okay, so we're going to do C. So let's start out with f prime of x equals 30x to the 4th minus 30x squared. So when I factor this and set it equal to 0, I can pull out a 30x squared. And then we're going to have x squared minus, what would this be, x squared minus 1? Is that right? Am I missing something? I think that's what it is. Yeah, that's what I get. Okay, so that's that piece there. And then now I look at this. This first one's going to be a quadratic root, but this actually splits into 2 linear roots. X squared minus 1 becomes x plus 1 and x minus 1. So 0 equals 30x squared. It's x plus 1 and x minus 1. So x equals negative 1, x equals positive 1, and x equals 0. But at x equals 0, I don't need to check that. I just need to check the other 2 because I don't really care about the other one. There's no sign change. All right. So let's see how we would do this. We'd take x and f prime of x, and here we go. So we're looking at negative 1, and then at 1. And this is how it's even cooler. You only have to plug in one number. Pick a number down here. Let's say negative 2. So you plug in negative 2. You get positive here, so that's positive. And then guess what happens after negative 1? Sign change, but that's below negative 1, and then, or below 1. And at 1, we're 0. And guess what happens at 1? Sign change. So it doesn't matter what numbers we're to plug in here between negative 1 and 1, or here after 1, because we know there's a sign change. Because there's a sign change. All we really had to do was look at what did we start with. Because we know then there's going to be a max at 0 and a min at 1, or a max at negative 1 and a min at 1. So f of x has a max at x equals negative 1 because f prime of x changes from positive to negative. Similarly, f of x has a min at x equals 1 because f prime of x changes from negative to positive. So now let's look at f double prime of x. F double prime of x. That's going to become, let's see, 120 and 60. So we got 120 x cubed and 60. Is this x squared or just x? X. So if we were to factor this and set it equal to 0, pull out a 60 and an x. And here we're going to have a, let's see, we got 2x squared minus 1. Ooh, that's a tough one to factor, but it does factor. It would wind up being square root of 2 times x plus 1 and square root of 2 times x minus 1. That's an advanced version of difference of squares, just because it uses square roots in it. So by factoring this completely, I would see that x equals 0, x equals, okay, this one, if I were to solve it, I would get a negative 1 over square root of 2. And for the other one, I would get a positive 1 over square root of 2. So what's happening there? Okay, notice this now. This is first degree, first degree, first degree, linear, linear, linear root. So what does that mean? Sign change, linear root of first degree or odd numbered root means sign change. So we know that f of x has points of inflection at x equals 0, x equals plus or minus 1 over square root of 2 because f double prime of x changes sign. Booyah. Alright, part D here. We are so close to the finish line. You guys don't even understand how close we are. In fact, let's peek at the finish line. How many more functions we have? We have these two, and then a word problem. And that's pretty much it. Okay, so let's look at this. We got to start with the first derivative. For first derivative, f prime of x. That first is going to become sine of x. And the second term there is going to become minus 1/2. So we got sine of x minus 1/2. When does that equal 0? 0 equals sine of x minus 1/2. Okay, so we got to move the 1/2 over. When does sine of x equal 1/2? Between 0 and 2 pi, of course. Well, if your knowledge of the unit circle is pretty solid here, we're looking at sine of x, which is the vertical measure in a unit circle. When are we 1/2? That would be the short pieces here and here. So we're at pi over 6 and 5 pi over 6 because we have to be positive 1/2. It's not negative 1/2. So x equals pi over 6 and x equals 5 pi over 6. Now the interesting piece here is that if you have a solid knowledge of the graph sine of x, think about it. These roots that we're talking about here are going to be linear, or they're going to go straight through. They're going to pass through. We're not going to have any bouncing off. So these are definitely going to have a sign change. A sign change of sine. That's an interesting way of looking at it. I almost wrote the word sign. Okay. This is the version now I was talking about. Okay, so what are we looking at then? Let's look at before and after. So we got f prime of x and f of x here, or not f of x, f prime of x and x, and we're looking at pi over 6 and 5 pi over 6. So if we were to plug in, let's say 0, well, that sine of 0 is 0. That's going to be negative. And guess what? This has got sign change in it. We're going to change to positive, and then back to negative. So we go down and then up and then down. So we got a min at pi over 6 and a max at 5 pi over 6. Excellent. Excellent, excellent, excellent. So that means f of x has a min at x equals pi over 6 because f prime of x changes from negative to positive. Similarly, f of x has a max at x equals 5 pi over 6 because f prime of x changes from positive to negative. Just kind of summarizing our findings there so we can prove that we actually understand them. Let's look now at second derivative. What would that be? That's, okay, there we go. Let's see what we have. Second derivative, we just take the derivative of sine, which is cosine. Derivative of negative 1/2, that goes to 0. So when does this equal 0? That's the question. Cosine equals 0 when x equals pi over 2 or x equals 3 pi over 2. And if your knowledge of the cosine of graph is good as well, you notice that you go straight through that x-axis. It's just straight through smooth. So we know that we have a point of inflection at x equals pi over 2 and x equals 3 pi over 2. So f of x, I should say, has points of inflection because f double prime of x changes sign. Excellent, excellent, excellent. All right. I think I'm actually going to finish with these two here. We're going to leave the word problem to tutoring, just because these online tutorials, we're kind of getting long on time here. So let's start out with critical values. So critical values, that means that f prime of x equals 0. So we're going to start with f prime of x. Remember that this function up here is really 4 times x squared plus 4 to the negative 1. So that helps us take the derivative a little bit easier. It means the derivative is going to be negative 4 times x squared plus 4 to the negative 2. And then the chain of that inside is going to be 2x. So now we multiply things there, simplify things. We get negative 8x on top and x squared plus 4 on bottom. So now we are considering more than one thing. We're not just looking at when it equals 0, but we're also looking at if it does not exist. Does not exist would mean denominator equals 0. And in this case, this denominator never equals 0. X squared plus 4 is always greater than or equal to 4, no matter what number you plug in. So it's never going to equal 0. So we're just going to focus on the top piece. Negative 8x equals 0, so x equals 0. Now think about this kind of root here. This doesn't have the exact same idea of a linear type root of a polynomial, so we have to actually check both sides. Oh my gosh, we got to do it the long way. X and f prime of x. So we're going to check before and after 0. So plug in a negative number. Let's say we plug in negative 1. Then this will be positive on top and positive on bottom as well, so that's positive. And if we were to plug in 1 afterwards, that would be a negative on top and a positive on bottom, so that's going to be negative. So we do have a sign change making this a max. So we would have f prime, or f of x, I should say, has a max at x equals 0 because f prime of x changes from positive to negative. Now let's consider points of inflection. This is going to be a little more complicated. F double prime of x here is going to be a quotient rule. Low d high minus high d low all over low low. So we're going to have x squared plus 4 squared on the bottom. And the low is x squared plus 4 times the derivative of the high, which is negative 8. And then we'll have, let's see, what else do we got here? Oh, we're not doing inflection points. Oops. Don't need to do that. Already done. Okay, this one. Wow, we thought it was going to be simple, but this is, again, a low d high minus a high d low all over low low. So low d high, that's so f prime is what we're doing. F prime of x equals, we got x squared minus 9 times 2x minus, we're going to have x squared plus 1, again times 2x. Then on bottom we'll have x squared minus 9 squared. So we got a lot of stuff going on in this one. Here's where, first thing that I see. This f prime of x does not exist when the denominator equals 0. So that's at x equals plus or minus 3. Definitely have to check out those things. And if I were to factor the numerator, so just the numerator piece, we're looking at, if we pull out a 2x, then we'd have x squared minus 9 minus x squared plus 1, but that negative gets distributed, so it's minus x squared minus 1. Then that would give me 2x times, well, the x squareds subtract each other, combining those, and we got negative 10. So it's going to be negative 20x. So essentially this whole f prime of x, if we were to simplify it, f prime of x equals negative 20x over x squared minus 9 squared. So x cannot equal plus or minus 3. And for this to equal 0, that would mean that x equals 0 implies that f prime of x equals 0. So we got to check 0, plus 3, minus 3, and all in between, because it's not the exact shortcut we were looking at the other one as far as roots that pass through. I have a feeling that things are going to be a little different this time. These squareds tend to throw us off. So we're looking at negative 3, 0, and 3. And of course before and after these as well. So let's look at before negative 3. Let's say 4. Well, that's going to give me a negative on top, but a positive on bottom. So if I were to look at negative 4, pardon me, that's going to be positive on top and a, let's see, positive on bottom. So that's positive overall. Then we don't exist, does not exist. Then between negative 3 and 0, so let's say negative 2, that would give us a positive on top. But down low, we would get a negative. So we got positive over negative. At negative 2, that's going to be negative. At 0, we're 0 again. Now if we plug in 2 this time, we get a negative on top, negative on bottom, so positive overall. Then plug in 4, we get a negative on top, a positive on bottom, so that's negative. So we do actually have sign changes. We got, a sign change here and a sign change here, and then a sign change there. So we got max, min, and max. So we would say that f of x, this is kind of interesting here. I can't even say x cannot even equal plus or minus 3 in the first place because that's not even in existence. So these terms here, I can't even use those. I should have seen that from the beginning. So then what's happening really, the only part that I care about is a min at 0. So f of x has a min at x equals 0 because f prime of x, here's the y, there's the where, now's the y, f prime of x changes from negative to positive. Excellent. All right. So that's it. Tutorial's done. We have this word problem here. I'm going to go over this in tutoring, or if you guys have questions, I'd like to go over it in class so we can kind of really analyze it deeply instead of just trying to explain it quickly here. So have a great break. We're number 1. Why? Because we're doing homework during break. You guys rock. Keep on rocking.